Hello, welcome to Harder Percentages 2. This follows on from Harder Percentages 1. We're going to deal with a couple of things. One of them is simple interest, then we're going to go into compound interest, and then look at percentage error. Okay, let's start by looking at simple interest. Well, the best way to look at this is to do an example. Here we've got Joe invested £5,000 in a bank which paid 8% simple interest at the end of every year. How much did he have in the bank after 10 years? Okay, so at the end of every year it paid 8% simple interest. How do we find how much he has at the end of 10 years in his account? Well, the first fundamental step is you've got to find 8% of the 5,000. This is 8% of the original sum invested. Well, change the 8% into its usual fraction of 8/100ths, and it's 8% of, the of changes into a multiply sign, and we've got this little bit of mathematics to deal with. And as you can see, there are some zeros on the bottom of the fraction here and some zeros on the top there. So we can cancel 1 0 on the bottom there with 1 0 on the top there, another 0 off the bottom there, and another 0 on the top there. This leaves us with a much simpler calculation to do, which we can even do in our heads. Is now 8 times 50. Well, you can cover up the 0 on the 50 and do 8 5s, which is 40, and put that 0 back on, and you get the answer 400. So 8% of £5,000 is £400. Now, so at the end of the first year, and at the end of every year for the next 9 years, he has this same amount, 8% of 5,000, £400. He has this same amount added on to his account. Now, that means, of course, that at the end of 10 years, let's get that into the center, there we are. So after 10 years, the bank has added 10 times 400. In other words, it's added on £4,000 to Joe's account. Well, if it's added on £4,000 to his account, then the total amount after 10 years must be this little easy sum here, £5,000, which is the original amount, add the total interest after 10 years, so he has in his account £9,000. Okay, that is the simple interest calculation. So simple interest just pays the same interest every year onto the lump sum that you originally invested. It's very, very easy. Okay, now let's move on to compound interest. Now this type of interest pays more because the interest is paid on the interest as well as on the lump sum that you originally invested. Okay, let me say that again. This does pay more because interest is paid on the interest as well as on the lump sum you originally invested. Now, I'm not going to explain that in words. I'm going to explain it using an example. I think that's by far the best way to do these sorts of things. Okay, so this time we're going to look at compound interest. Now, Jasdeep invested £6,000 in a building society which paid 7% compound interest annually. How much did Jasdeep have in his account at the end of 3 years? Okay, so there we have it. We've got an original amount of £6,000 being invested at 7% compound interest, and it's compounded annually, so at the end of every year. And we want to know how much would he have at the end of 3 years. Well, we do it in steps, yearly steps. Okay, so the first step is we look at what he has at the end of the first year. So we have to find the interest paid at the end of the first year. So what we are calculating is 7% of 6,000. The of will turn into a multiply sign, and the 7% will turn into a nice fraction like that. Again, we have zeros on the bottom and zeros on the top, so I can cancel 1 0 there with 1 0 here, another 0 on the bottom there with another 0 on the top there. So I now have the calculation 7 times 60. Well, I can cover up the 0 on the 60, and I've got 7 times 6. Well, 7 times 6 is 42. Put the 0 back onto 42 and you get 420, and that is exactly the answer. So at the end of the first year, the £6,000 has increased by £420. Okay, so the total amount he has is now, this is interest is now added on to the original to give £6,420. So this is the amount he has at the end of the first year. The interest is added on. I've done it in red here. Now, at the end of the second year, we have to find the interest paid on this increased sum of 6,420. Okay? So we perform the same calculation now, but on this slightly increased amount. So here we have it. At the end of the second year, we must again find the interest paid, and that means this time finding 7% of the increased amount. This is the amount at the end of the first year, £6,420. So again, we change this little statement of 7% of this into a little bit of mathematics. The 7% becomes 7 over 100. The of sign becomes multiply, and here we have this amount at the end of the first year. If we do that, we can use a calculator now. We get the answer £449.40. Now this is now added on. Okay, this interest, this is the interest at the end of the second year, is now added on to the 6,420 to give this new sum £6,869.40. This is the total amount he has in his account at the end of the second year. Now, at the end of the third year, we have to find the interest paid on this new sum, this increased sum, this sum at the end of the second year. Okay, so we do exactly the same calculation at the end of the third year. Okay, let's get that in the middle. There we are. So we are finding the interest paid on this new amount, 7% of £6,869.40, and again we're performing the same calculation. The of becomes a multiply, the 7% becomes 7 over 100. We can do this on a calculator. 7 times this, all divided by 100, and you will get this amount here. This is the interest he has earned at the end of the third year, and this now gets added on to that sum he had at the end of the second year, this £6,869.40. Okay, so the this interest is now added on to that sum there to give the final amount after 3 years, and there it is, £7,350.26. I've rounded it up to the nearest pence. Okay, so at the end of every year the interest was added on and the new sum was found at the end of the next year. That is basically what compound interest is. Now, as you can see, let's get that in the center. There we are. As you can see, finding the interest at the end of each year and adding it on can be a bit long-winded. In that example we've just done, we only did it for 3 years. But imagine if you wanted to find the final sum at the end of 10 years. Well, a thing like that would take forever. That method I showed you would take 10 steps. And let's hoping that during those 10 steps you made no arithmetical mistakes. So, is there a quicker method? Well, there is. There's a very, very neat and useful formula which can save you a lot of time. That is, if you know how to use it. Now, this formula looks a bit daunting, but I will explain it in a second. Okay, there's the formula. Gasp, gasp, what a horrible looking thing. In fact, it's very easy to use. Alright, I'm going to explain it right now. Alright, now let's get that down here. There we have it. Alright, now I'll deal with the first two parts first. This A with a little n at the bottom here, this is the total amount you will have at the end of n years. So in that last example that I was doing, this little n would have been 3. Okay, but don't worry about that. This A is the original amount that you invest. Okay, now this R and this N are the only other two things you need to know about. Okay, now the R is the percentage compound interest, and let's get that more in the center so you can see it. There we are. And this N is the number of times the interest is compounded. Now normally the interest is compounded at the end of every year. It's an annually compounded. Okay, so in other words, if the interest is worked out at the end of each year, then N is just the number of years. Okay, now this N is a power to which this brackets is raised to. So you'd have to work out inside the brackets first, raise it to the power, and then multiply your answer by A. Alright, now it looks a bit daunting, but as I said, but I'll give you an example and you'll see how easy and how powerful this formula is. You can use this formula, by the way, even if you want to calculate the compound interest just after 3 years. But if you have more than 3 years, 4 years, 5 years, 6 years, then it is a very quick and powerful formula to use. Okay, now what we'll do, we'll look at the last example, this time using the formula. Okay, so here we go. As an example of how to use it, let's do the example above where Jasdeep invests £6,000 at 7% compound interest over 3 years. Okay, so how do those numbers fit into the formula? We want to find A3, that thing. It's just the amount he has after 3 years. That's what you've been asked to find in the question. Okay, so here we have the formula with the figures in. 6,000 is the original amount that goes in front of the brackets. The 1 is there, and you're adding 7% and the whole thing is raised to the power of 3, the number of years over which the interest is compounded. Okay? Now, it's very important that this 7% is changed into either a fraction or, even better, a decimal. I've done it in both steps to make it absolutely clear. I've changed the 7% into 700ths, and then I've changed the 700ths into a decimal, and 700ths is 0.07, and 0.07 add 1 is this thing here, 1.07, and it's all raised to the power of 3. Now this little bit here I've written in pencil is to remind you of how useful the power button is on your calculator. Now you could, if you were unsure how to use this power button, you could put 1.70 times 1.70 times 1.70 to get 1.70 to the power of 3. But this is a much more powerful way, or quicker way of doing the same calculation. You would key in 1.70 to your calculator, then you would press this button, this power button, and then you would press in 3, and then you would press equals, and it would give you the same answer. This, by the way, is a much quicker way. Using this power button is a much more quicker way. If this power here, instead of being like 3, was something like 7 or 10, this would be a much quicker way of doing it. Okay, well, what is 1.07 raised to the power of 3? There it is. It's 1.225043, and we have to multiply this now by 6,000, and we get immediately the correct answer. I've now done it, yes, there it is, to the nearest pence, 26 pence. £7,350 26 pence is the amount Jasdeep has in his account at the end of 3 years when compound interest is paid at 7%. We've got there using this formula in about, well, let's see, 1, 2, 3, 4, 5, 6 steps. Alright? Very, very useful formula indeed. Well, being a mathematician, I like formulas which are powerful, and this formula is even more powerful. Okay, let's show you what I mean. Let's supposing you are told that a new car loses 8% of its value every year. How much would a brand new car costing £15,000 be worth after 7 years? Now we can use the same formula, with a slight change in it, to calculate a thing like this. We could, of course, find 8% of the brand new price and take it away from the brand new price to find that the reduced price at the end of the first year, and keep doing this every year for 7 years, but it would take us forever. But we can use this formula. Watch. I'm going to put in to the formula these figures, and here it is. We want to find A7, the value of the car after 7 years. Alright? Now, who can spot the difference in this formula to the last one? There's my original amount, £15,000. There's my percentage, 8%, and it's over 7 years. Yes, you've all spotted it. There is the big difference. This is now a minus sign, a takeaway. And why? Because the value is being lost each year. Okay? So we now turn this into a little bit of mathematics. Okay, let me get that in the center. There it is there. I've changed the 8% percent into its fractional form, 8/100ths, and then I've changed that into its decimal form, 0.08. okay, the minus sign is still coming through, okay, because the value is being lost. And if we take this 0.08 away from 1, we get 0.92, and this 0.92 is being raised to the power 7, and really it's a must that you use the power button to calculate this to the power 7. Alright, so you would key in 0.92, then press your power button on the calculator, then key in 7, press equals, and out would come the answer 0.5578466, which you now multiply by the original amount. That was the original cost of the brand new car, and there is your price at the end of 7 years. Okay, or to the nearest pound, £8,368. And we've done this in about 1, 2, 3, 4, 5, yes, about 6 steps. And really, it's by far the most efficient way of doing a calculation like that. Okay, so in summary, we can do this. We can say this. So for compound interest, this is when value is gained, we use that formula with a plus sign. Okay? The amount after n years, the original amount, percentage compound interest, n number of years, but this is plus because value is gained. Alright? Compound interest. But for value which is lost at a certain percentage per amount of time, usually per year, you can use the same formula but this time with a minus sign. Very important difference. Okay? However, do remember please that if the percentage is, for example, this is just an example, if the percentage is 9%, you do not write R, okay, you do not write R as the number 9, okay, you convert the percentage into a fraction, or better still, into its decimal form, so that 9% would be written as 0.09. It's this that you would either add to the 1 in the brackets or take it away from the 1 in the brackets. Okay? Right, well that covers an example or two of the compound interest. Now we're going to finish off by looking at what we mean by percentage error. Now, when scientists and engineers make measurements, they often need to know something which they call the percentage error of their measurements. Okay? And I think the best way to look at this is to go straight into an example. And here I have example 1. A length of motorway supposed to be exactly 1 kilometer long, but when measured it is actually 998.72 meters long. Okay, so it's supposed to be 1,000 meters long, 1 kilometer long, but when they measure it, it's actually 998.72 meters long. Okay, well, find the percentage error in the length of the motorway. Well, your very first step is to find the difference between what the length should be, which is 1,000 meters, it should be a kilometer long, and what it is measured to be, what it actually is, 998.72 meters. So to find the difference between those two, you of course have to take one from the other. Okay, there it is. I'm taking the 998.72 meters, the actual distance away from what it should be, 1,000, and there it is, 1.28 meters. That's the discrepancy or the difference between the real one and what it should be. Okay? Now you ask the question, what percentage is this 1.28, this difference? What is the percentage of what the length should have been? Okay? i.e. of 1000. What percentage is this 1.28 meters of 1000 meters? And that is really the percentage error. So what we do is we make the fraction. Okay, you make the fraction 1.28 divided by 1000, and then you multiply by 100 to find the percentage error. So you're dividing the difference by what it should have been, and then multiplying by 100, and here we have it. Okay, so that's the calculation you would do, and if you do this, you will see that you can change this decimal here, because you're dividing it by 1000, 3 zeros in 1000, so this is going to jump 1, 2, 3 places that way, giving this decimal here, and then the whole lot is multiplied by 100, so the decimal point comes 2 places back that way, and the answer is 0.128%. That is the percentage error. I could of course here have crossed off 1 0 there, 1 0 there, with 1 0 here and 1 0 there, leaving me effectively with 1.28 divided by 10, which would have given me the same thing here. Okay, let's do one more example of percentage error before we finish off. Okay, this one concerns a shop that sells carrots in 5 kilogram bags. Helen bought a bag and found that it actually weighed 5.12 kilograms. What is the percentage error in the weight of this bag? First step, find the difference in the weights. Okay, find the difference in the weights, meaning find the difference between what it actually is, 5.12, with what it should have been, 5 kilograms, and the difference comes out at 0.12 kilograms. Now we ask, what percentage is this difference, this 0.12 kilograms, of what the weight should have been, i.e. it should have been 5 kilograms. Okay, let's get this in the center. There we are. What percentage is that of what it should have been, 5 kilograms? So we make the fraction 0.12, that's the difference, divided by 5, and then we multiply by 100 to find the percentage error. And there's the little piece of mathematics that we get our teeth into. There's the difference, there's what it should have been, and we're multiplying by 100, and that comes out at 2.4% as the percentage error in the weight of the bags. Now, in general, we can look at it like this. Okay? In general, let's get that in the center so you can see it exactly as it should be. There we are. The percentage error is something called this ratio here. It's the absolute error divided by what the value should have been, the whole thing times by 100. Now I'm going to explain what this absolute error means, okay, because it looks a bit awful, but it's really a fancy word for what we've just actually done. Okay, the difference between what the measurement should be and what it actually is given a special name. It's called the absolute error. Okay, so this thing up here on the numerator of this little fraction up here, this absolute error, this is really just what we've been finding, the difference between what it should have been and what it actually was. Okay, but it's called the absolute error. Now, the word absolute means you've just got to make sure you take the smaller number away from the larger number so that the difference is always positive. Yeah? So in other words, this is called the absolute error because we always take the smaller number away from the larger number to make sure that this numerator has a positive value. That's all it means. But this is just the difference in between what the measurement actually is and what it should have been. Okay, well that concludes harder percentages 2. I certainly hope that you've managed to understand and practice a few things for yourselves when I've finished, and then I'm sure it'll all fit into place. Okay, thank you very much.